Welcome. In this video, we will begin discussing the scattering or S matrix. This is a very important concept to understand, and even though in this course we will not really go into it much more, it is good that we have at least a little bit of an introduction, because in the end, studying scattering is literally what physics is about, especially modern day physics, like what is done at the CERN, for example, because what you do is you just send a bunch of particles into each other and then you study the scattering process. And although it is, of course, much more complex than what we see now, in essence, it is scattering. And what you want to identify is indeed the scattering matrix, which is what we'll now begin to introduce. So this concept will appear over and over again as you go into higher level courses. So let's begin discussing it. So let's just consider a general case where we have some potential in a region. So we have a region where there is no potential, and then we have, so this is region 1 with no potential, and then this is potential as a function of x, of course, and then in the second region we have some potential. Now it's anything, right? It could be anything, positive, negative, I have no idea, something, right? But there is no potential in the other regions, only in this region. So this is region 2. And then we have a third region with no potential. So the waves that we could have is, here we could have some incoming wave, AEI kx, some reflected wave, BE minus I kx, this of course traveling to the right, this to the left. And we could also have a wave traveling out, so FEI kx, and we could also have a wave coming in, GE minus I kx. So this is coming in and this is going out. So that is basically everything that could be happening. And let's put it all together into a wave function, right? So we got AEI kx plus BE to the minus I kx for region 1. And then in region 2, we don't really know, but we have C times some function of x plus D times some other function of x. Let's call it g of x, right? This is in very, very broad terms. This is for any potential. So this could be anything. And then we have the outgoing part, FEI kx plus GE minus I kx. And then just as we have done very often, maybe we want to find the transmission coefficient, maybe the reflection coefficient. So what we usually do in those cases is that we begin to apply border conditions, right? That is what we would usually do. We are studying this very general case, and then we apply we find the wave function, we apply border conditions. So when we do that, what we usually do, because we are interested either in f, right, the outgoing coefficient, or maybe in B, the reflected one, right? If we find F or T, depending on what's going on. But the point is that we don't really care about C and D. We usually just eliminate them because they are not really what we measure. It's not what we put in and it's not what we measure. So we don't really care about it. It's just something in the middle. So for that reason, what we usually do is that we find A, or basically we find B, right? Which is the reflected coefficient, as a function of something times A plus something times G. Now, we usually have set G equal to 0 because we have been working with scattering from the left, but we are just in a very general term. And then F would be also something times A plus something times G. And this something we have seen, for example, in the past, stuff like 1 plus IK over L, for example. We have seen something regarding like exponentials, and there's a lot of possibilities. But just in very general terms, we are going to call it S11, and you will see why that name. We'll call this S12. It's simply some constant, and this is S21 and S22. So this is what we have been doing the entire time. We're simply taking the procedure that we used to do and just generalizing it, right? And we can now write these two equations as a matrix equation. So we have BF is equal to, and now we have S11, S12, S21, S22 times AG. And you can, of course, multiply this through, and you will see that this is indeed correct. And this matrix here is what we call the S matrix, or the scattering matrix. And why is this relevant? Because as we will see, this matrix contains all the information that we need for this problem. And oftentimes, we will be able to solve things much, much quicker by using this matrix. So let's now look at a few examples, or like in general, what happens if we are dealing with scattering from the left. So that means that G is equal to 0, right? Because G represents an incoming wave from the right. So in that case, when G is equal to 0, we can see from these equations immediately, if it is a bit hard to see from here. But either way, whether you want to see it from these two equations or from the matrix form, what we get is that B is equal to S11A and F is equal to S21A. So this means that the reflection coefficient, right, which is B over A squared, is simply S11 modulus squared. And the transmission coefficient is F over A squared, which is, of course, S21 squared. So we can see that if we can write our system in this form, which we usually can, then we, just by forming this matrix, we already know the coefficients. So that is pretty useful. This is, of course, in the case G is equal to 0. We can do the same in the case where A is equal to 0, which is scattering from the right, which we haven't done so far. But it doesn't really matter. It's simply a difference in the side that you're doing it from. But in that case, you're going to get, instead of S11 and S21, you're going to get S12 and S22. So it is the exact same thing in principle. Just to be thorough, let me show you what it is explicitly. So the reflected coefficient in this case, so if G is incoming, so let me maybe take a look at this. So if G is the incoming wave, then F is the reflected one, and B is the transmitted one. So that means that the reflection coefficient this time is going to be, now G is our incoming wave, F is our reflected one. So this squared, which is, let's see, so if A is equal to 0, here, for example, we can see that F over G comes from here, so that is S22. So this is S22 squared. And the transmission coefficient comes from this, so B over A, which is it's B over G, so it's 1, 2. This is B over G squared, and this is 1, 2 squared. Okay, so we have seen, just broad thing, and this is already quite a bit. But now, let's go see why this is like even more powerful. Because not only can we get information about the transmission and reflection coefficient, but we can also get information about the bound states, if they exist. Of course, they don't necessarily exist. But let's say that they exist, or we want to check if they exist. So we want to know if there are bound states, right? Where the energy is less than the potential. In this case, we can say less than 0. And in that case, we can form our wave function again, right? Let's go for now a more specific case. And now in this case, in region 1 and 3, we don't really have traveling waves because we are in a bound state. It's not a scattering state, right? This right here was scattering state. Now we are in a bound state. But the scattering matrix still can give you information about the bound states. So that is really interesting. So this time, we have something interesting that in the first region, basically in a region where the x are negative, we get be to the kx, right? With, of course, k, let me move this, being square root of minus 2me over h bar, which is of course something we have seen before. In region 3, we get something similar, just fe to the minus kx. We cannot allow the other options. We cannot allow a and g because they blow up, right? In the negative x, if we have an option with ae to the minus kx, for example, it just blows up. And then we have in the middle, again, something, right? cfx plus dg of x. We have something in the middle. Now, notice that we have the exact same structure as before, right? The only difference is that now a and g are 0. So that means that we can use the exact same results that we already have, but this time, of course, take our values of a and g to be 0. Notice, too, that before, when we were here, even though we didn't say it explicitly, but we were in a scattering state, so our k was not minus 2me, it was square root of 2me over h bar. So basically what I'm saying is that our new k is basically I times our previous k. So we used to have k, and now in the bound state, we have ik. So that is the only change that we need to make in order to use all of this procedure, but for bound states. Well, I guess not that part, of course. So let's now use that. So let's take a look at this, at the scattering matrix. Now, we know that BF is equal to the scattering matrix times AG, but we just said that A and G are both 0 in this case, right? So we know that BF is equal to the scattering matrix times AG. But if AG are both 0 and BF are very much not 0, then this will have to be infinite so that we can get an undeterminate result and we don't get some sort of contradiction. So basically what we are saying is that if bound states exist, and this is the important part, if they exist, then we need the elements in the scattering matrix to blow up. That is what we are saying, right? So let's just do a quick example. Now, something that we have seen before is that we found in the case of the finite square well, we found it to be, or actually we found rather f over a, which is what we defined as S21, we found it to be e to the minus 2i ka. We did this a few videos ago, so if you're unsure, you can go back to my video about the finite square well, which is in the same playlist as this one. Sine 2la divided by 2kl k squared plus l squared. Okay, so we want this to blow up. Now, how can we do that? Well, for this to blow up, right, because this is one of the elements of the scattering matrix and we need it, right, we need it to go to infinity. And for that, this part needs to be 0. So basically, the cosine of 2la minus I sine of 2la over 2kl k squared plus l squared needs to be 0. And we need to impose that since we are no longer in a scattering state, now we are in a bound state, our k goes to ik. So this k right here is now, so to ik, and this k right here is now ik, so we get minus k squared. So I'm going to write it as l squared minus k squared. Okay, so the i's cancel out, and now we want to see, well, what condition do we get from this? So we can divide by sine, so we get cotangent of 2la. This is equal to l squared minus k squared over 2kl. And, well, this is already a condition for the energies and stuff, but we don't really have, it's not really an explicit formula. It's got the cotangent. It's a bit hard to work with. L squareds we would like to simplify it. And for that reason, we can use the following trigonometric identity, which says that the tangent of some angle over 2, where this is basically the half angle formula for the tangent, is 1 plus cotangent squared of theta minus cotangent of theta. And this is very useful because if we now plug in theta is equal to 2LA, we get tangent of LA is equal to plus or minus square root of 1 plus this thing squared, so L squared minus K squared divided by 4K squared L squared, and then minus L squared minus K squared divided by 2KL. So now let's simplify this a little bit. So the left-hand side remains the same. This is plus or minus square root of, and now 4K squared L squared, I'm taking common denominator here, plus, now let's expand the square. We get L to the 4th power minus 2K squared L squared plus K squared. And all this is divided by 4K squared L squared, which is 2KL. Okay, and now this other part will be the same. So minus L squared minus K squared over 2KL. And notice that in here, this and this cancel out a little bit. So we get plus 2KL squared, which is simply L squared plus K squared squared. So we can take the square root and we get that the tangent of LA is either plus or minus. Then we get L squared plus K squared divided by 2KL minus L squared minus K squared divided by 2KL. So now we have two cases. So let's go for the positive. So in that case, we get tangent of LA, and this is L squared plus K squared divided by 2KL minus L squared minus K squared divided by 2KL. And here we see that the L's cancel out. We get 2 times K squared, so 2K squared over 2KL, which is simply K over L. Thus, we got the condition that tangent of LA, that is the same as K over L. And it's important to note that Griffith's book in the 3rd edition makes a mistake. In the 3rd edition, it says that the tangent of LA is equal to L over K. And that's what it says in this section. However, previously when we did this, we did get the correct result, right? It is equation 2.136. There we do get to the correct result that the tangent is K over L. So if you were wondering why it looks weird, it is because Griffiths got it wrong. At least there's probably a typo there. Okay, so that is the plus sign. Now we can do the same for the minus sign. So we get that the tangent of LA is, and now, well, we get a minus in front. So this time we get minus L squared minus L squared. So we get minus 2L squared. And we get minus K squared plus K squared. So this 2KL. And this is the same as minus L over K. And we can, just to make sure that it's also in the form K over L, we can write it as cotangent of LA. So basically we divide with 1 over this equation, and there we get minus K over L. And this is the result that we got previously. And these are the conditions for the energies. So this is very interesting. So you can see that using the scattering matrix, we found in a much faster way the exact same results that we found previously for the bound states. So this just shows you the power of the scattering matrix, and we haven't even begun to scrape the surface. So what you have to keep in mind is that this is what a scattering matrix looks like. Deriving it is very, very simple. And yeah, keep in mind that whenever you want to find the bound states, if there are any, right, if the scattering matrix doesn't blow up, if there's no way to make it blow up, then there are no bound states, right? And then you just, if you can, you have to use this condition, k goes to ik, right? Because now our energy is negative, so the k changed. So there we go. I hope this was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe. And, maybe share it with some of your classmates. And if you really enjoy the content, maybe consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.